So good Monday afternoon, everyone. Welcome to lecture 20 of Maths for Construction. Just a review, last time we did some simple combinatorics, which is counting principles, mainly permutations and combinations. Combinations are important because they will show up in the binomial theorem, right? So we went through factorial, different distributions. What is a distribution, right? With a discrete random variable. We covered that. We did some distributions of different discrete random variables. And we met the most important discrete distribution there is the binomial distribution. Okay. With some formulas so that the idea behind this is you have a bunch of independent trials and the probability of success is the same in each trial. What will happen is a discrete random variable will arise, which tells you how much times a success would happen. Okay, that's what we were talking about here. So moving on to lecture 20, we talk about the binomial distribution. You have a number of successes. That's what X is. X, that variable, that discrete random variable is how much times you have a success in N trials. So an example is, you throw a die 3 times. How many times would you get a 6? Right? You could, out of 3 times, you could get a 6 0 times, meaning you never score a 6. You could get a 6 once, you could get a 6 2, and you could get a 6 3 times. You have 4 possibilities. So there's a discrete variable X, which is the number of 6s that has the values 0, 1, 2, and 3, and we have a probability for each one. Right? The chances of you getting 1 6 is different from 2 6s, is different from 3 6s, that kind of thing. You get a distribution of probabilities, a probability for each value of X, right? So rather than doing probability distribution tables like how we did here for our entire distribution, we realize there's a formula that tells you what the probabilities are. Okay, so here we have an example. Was you obtaining a head? So you throw a coin, you could get head or tails. But the coin is biased. It means that the chances of getting a head is 2/3, right? Not a half, as an unbiased coin would be. You toss a biased coin 4 times. Find the probability of obtaining exactly 2 heads. Okay, so the solution is, you consider the chance of obtaining a head success, right? That outcome is a success. So in 4 trials, each trial is independent, each experiment is independent, meaning the outcome of one does not affect the other, right? So the outcome of the 3rd experiment don't affect the outcome of the 4th experiment, right? So that's how the independent trials. You toss a coin 4 times. The chances of getting a head is 2/3. What's the chance of getting 2 heads? Now, one way of getting 2 heads is shown here. You get a tail and a tail, then a head and a head. Okay. Each of these 4 probabilities, we multiply them because they're independent events. This is the probability you're getting a tail the first toss. This is the probability you're getting a tail in the second toss. This is the probability you're getting a head in the 3rd toss. And this is the probability you're getting a head in the 4th toss. These probabilities don't affect each other. Head is still a head, right? So you get not getting a head squared by getting a head. But this is one of the several ways to get 2 heads. You could get 2 heads like this. What if you got a tail, a head, a tail, a head? That's 2 heads. What if you get a head, 2 tails, and a head? That's still 2 heads. What if you get 2 heads, then 2 tails? That's still 2 heads, right? And I have a couple others. So combinatorics to the rescue, combinations. How many ways in 4 trials could you get 2? Right? That's 4 choose 2. Okay, that's what we call it, 4 choose 2. So out of 4 options, how much ways can you pick 2 options? Right? So how much ways you could select 2 things out of 4? And when they use words like pick and choose and select, I mean combinations, not permutations, not patterns. So the chances of getting two heads exactly is the probability of getting two heads multiply the number of ways of getting two heads. I have 6 ways to get two heads out of 4, right? And this is the answer here. This is revision from last class. So we have some notes that we could write to help us along, right? So this was speaking specifically. So so generalizing. So suppose the probability that an experiment results in a successful outcome is P. This is one experiment, okay? You have one experiment and the idea of success, the chances of that happening is P. The probability that it's a failure is 1 minus P. That's just the opposite, right? Because the probabilities have to add up to 1. Now, if X is a random variable, that's what this RV is here, random variable. The number of successful outcomes, right, in n independent trials. Independent is important as well. So successful outcomes in n independent trials. So it means you repeat the experiment n times. Each time there's a probability P that a success would happen. So then the probability density function is given by this here, this formula here. Okay. So n choose A, right, by probability of a success to the power A by probability of a failure to the power n minus A. And this formula is true for different values of n, right? A is the value that X can have. X can have different values, right? This should be A, sorry. Right? A can have different values. There's a discrete variable, right? There's a discrete variable. So X could go 0, 1, 2, up until n because you have n trials. So how many times you could get a success in say 3 trials? You could get 0 successes, 1 success, 2 success, or 3 success, okay? Each value of X is associated with a distinct probability of that value happening, okay? If you rearrange this equation here, well, not rearrange it, if you, you know, substitute for Q, you get this formula here. And you could take out the multiplication signs, right? But I find it might look a little too jumbled up if you don't do it. So if X is distributed in this way, we write X, that this little squiggly line here, this little tilde character here, kind of like approximate, but 1 instead of 2. We say X is distributed binomially with parameters n and p. And the parameters are stated in order, n first, then p. Okay. So n is the number of independent trials, and p is the probability of successful outcome in one trial. N and p are the parameters of the distribution, and how you read the statement here, X, this highlighted statement, how do you read that? Oops. You say X follows the binomial distribution of parameters n and p, as I just said, right? So this is the general idea behind the binomial distribution. It's a discrete distribution for a variable X. X can have discrete values. X is the number of successes in n independent trials. P is the probability of a success in one trial, n is the number of trials. The formula for the probability is given by this formula here. So we could try a question. So look at this question here. The probability that a person supports party A is 0.6. Okay. Find the probability that in a randomly selected sample of 8 voters, there are exactly 3 that support A, at most 2, and more than 5. So the idea is you have 8 voters in a group. What's the probability that one of them support party A? 0.6, right? But now you have 8 of them. So you're repeating a process 8 times. Those are the 8 independent trials. Probability of success does not change. It's still 0.6 for each trial. However, when you perform all the 8 trials, you want to ask yourself, what's the chances, what's the probability of X having a certain value? X, of course, is the number of people who support party A. You could have 0 of them, 1, 2, 3, up until 8, right? So this is a fit for the binomial distribution. Tell me if you think you could work out the first part, exactly 3. Right? What we will do in the solution, we will say, could say something like this. Consider supporting party A as a success. So the experiment is you ask somebody if they support party A, and a success is yes. Okay, so that's one experiment. Now you're repeating that 8 times with 8 people, and you're asking them, do you support party A? Do you support party A? And they get yes or no answers. The question is, what is the probability of exactly 3 of them saying yes? Well, what that is an experiment of 8 independent trials where the probability of success in one trial is the 0.6, right? And you want to know how much successes. So if X is the number of successes, the number of party supporters, X is a random variable. It could have values 0, 1, 2, 3, up until 8. You follow? So X is binomially distributed. Could write something like this here. X is distributed binomially with parameters 8 and 0.6. N is the number of independent trials. It's independent because one person supporting a party doesn't really affect another one. We're assuming that, right? We know people could change their mind on these things. So we get this here, and then we could substitute into this formula here the values of N and P. So N is 8, N is 8, and P is 0.6, and Q is 0.4, right? N is 8 again. Let me put 8 here. Right? So this is the formula. This is the probability that X equals to 8. What do you think would be the answer for the first one? And think about what does the second and the third one, what is it asking you? They're asking for more than one value here. All right, think about it. X is a discrete variable. If this is asking, what's the probability that X is more than 2? How would you find that out? Sorry, at most 2, right? So it'll be less than 2. This one is more than 5, right? How many of these would you need? Think about it. Work out the first one and think about the second 2. Okay, so the first question, if they want to find a probability, you have 3 voters. X is the number of voters, right? The number of people that support party A. So essentially what they're asking you for here in the first part is the probability that X equals 3, right? What's the probability that X equals 3? So A will be the value 3. So we put 3 inside of here, 0.6 cube, 0.4, 8 minus 3, right? So that's 0.4 to the power 0.5. Sorry. Right. Now, 8 choose 3 does 8 factorial over 5 factorial by 3 factorial. So the 5 factorials will cancel to give 6, 7, 8. And that's 6 by 7 by 8 over 3 factorial, which is 6. So that's 7 by 8, which is 56. Right? So there's 56 times 0.6 cube. Could work that out here. Six cube is 216. So 0.6 cube is 0.216, right? And 0.4 to the power 5, let's say 0.4 to the power 5. Zero, 10, 24. Multiply 0.216556. So we can give our answers to 3 decimal places. So that's 0.124. Right? This is the probability that 3 voters out of the 8 supports party A, right? The independent trial is asking somebody what if they support party A or not. Is this success or failure, true or false, right? Each experiment has a kind of true or false situation where true is you got a success, false is you got a failure. That's why it's binomial. Bi means 2. Each experiment, there's only 2 possibilities, success or failure. But you're repeating the experiment a number of independent times, 8 times in the sense. So if you have 8 experiments, how many ways could you have 3 successes in 8 experiments? Does 8 choose 3, right? You make 3 choices out of 8. Right? That's 56 possibilities where you could choose 3 from 8. And then you multiply that 56 by the probability that somebody is a supporter, right? In that occurrence. So it means 3 successes. It means P, the probability of a success would have been multiplied by 3. And then 5 of these events had a failure. So multiply by 0.435. Remember, it's in 8 independent events. And you're multiplying 8 probabilities. These are 8 probabilities here. 3 of them is success and 5 of them is failure. And there's 56 ways you could get 3 successes out of 8. Okay, so that's what this is here. What do you think the second question is? They say at most 2 voters. What does that mean? At most 2. What do you think at most 2 means? It had to be X. We had to phrase it in terms of X. X is the number of voters that support party A. So if at most 2 voters support party A, they're asking what is the probability that X is less than or equal to 2, right? Because they say at most 2. You could have 0 people that support, like if you have 8 people and you ask all of them, okay, do you support party A? 0 of them could say yes. Means you have no successors. So this could be 0 or 1 or 2. So you have to phrase it in terms of the original question. So we could have probability X equals 0 or probability X equals 1 or probability X equals 2, right? Why are we using or? Right? Because they're mutually exclusive, right? They can't occur at the same time. If you ask 8 people if they support party, you can't have 3 of them saying yes at the same time, 4 of them saying yes, right? It's mutually exclusive. The chances of 0 successes is mutually exclusive from the chance of 1 success. They don't occur at the same time. So that's the OR rule. Remember the OR rule for probabilities, right? You could just add them, right? They're not mutually, if they're mutually exclusive, you could just add them. If they're independent, the AND rule is you multiply them. That's something else, right? That's asking for AND. But you can't have 2 successes and 0 successes, right? It's not possible to have both of them occurring at the same time. So that's why I could add the probabilities. This probability is the probability that 0 successes. This is the probability that you had 1 success, 1 person like party. And this is the probability that you have 2 people that support party. All right, so what I want you to do now is calculate what this probability is here, right? And then think about what question 3 is asking. Phrase it in terms of this probability here and try and figure it out. So they say at most 2 voters. So at most 2 means 0, 1, or 2, right? So 0, 1, or 2 is this probability here. This is the probability as 0 voters support party. There's 1 of them and this is 2 of them. They can't happen at the same time, so they're mutually exclusive. So or means you just add them. You have no intersection. We did that, you know. If you go back to, let me see. Where are we at? Was it lecture 18? Yeah. Right, for mutually exclusive events, the intersection is 0. So, or probability A or B, you just add the probabilities, right? So here now, I have this formula 3 times, okay? So I'll take my time and do this. So I'll take out the times and just write it like this. So 0 for 0, A would be 0. So the lower bound is 0. P is 0 and 8 minus 0. Okay. Plus, where's the correspondent for 1? 1 is here, 1 is here, and 1 is here. This one, 2 is here, 2, 2. Right? So you see P is the probability of number of successes. So this is one success, this is two success. And then if you have two successes, you're gonna have 6 failures. And is we and in those probabilities, so we have to multiply them because they're independent. What is 8 choose 0? That's 8 factorial over 8 factorial by 1. By 0 factorial, right? Which is 1. So we could try, we could say, you know, any number like say 5 factorial divided by 0 factorial equals, and then you divide that by 5 factorial. So it's 1. And this makes sense because it have only one way to have 8 failures, right? It means everybody failed. So this here, this is 1.6 to the power 0 is 1. Right? And this 0.4 to the power 8. This one down here, 8 choose 1. This is 8 over 7 factorial by 1 factorial. This is going to be 8. Right? I'm going to be 8.6. You don't need that power. And this is 7. And 8 choose 2. This is 8 factorial over 6 factorial by 2 factorial. So 6 factorial will cancel to give 7 by 8 divided by 2. That's 7 by 4. So this here is, there are 28 ways. And this is to the power 6. Right? Continuing to simplify this. So 0.4 to the power 8. 0.4 to the power 8. Right? This is a real small number here. Right? But that is essentially what this is here. You're really just calculating it at this point. Right? 0.4 to the power 7 by 0.6 by 8. So 0.4 to the power 7. Right? Then this one, 0.4 to the power 6. Multiply 0.6 square, multiply by 20. You can add up these things, right? So the 3 decimal places is essentially that. Because 3 places, default places are 8. So this turns in 9 and the 49 to 50. So you're 0.05. So it's like 5% of the time you would expect that you have at most 2 supporters in a group of 8. That's what this is doing here. Right? What about this question here? More than 5 voters at support party. What is more than 5? X is more than 5. That is all, right? So what are the possible values X could have if the value must be more than 5? It could be 6. It could be 7. It could be 8. Right? X is a discrete variable. X is the number of people that support the party in a group of 8. You can't have more than 8 people supporting a party in a group of 8. You know what I mean? X could have discrete values 0, 1, 2, 3, 4, 5, 6, 7, 8. What's the chance that more than 5 people support the party? Doesn't include 5. So that's 6, 7, 8. So we could do something similar to this here. Chance is more than 5. So again, this is a 6, 6, 6. This is a 7, 7, 7. And this is a 8. 8 successes. Right? See what happening here? This is X equals 6. See 6, 6, 6, 7, 7, 7 for 7 and 8, 8, 8 for that. So what is 8 choose 6? 8 choose 6 is the same as 8 choose 2. Right? Which is 28. 28 times 0.6 to the power 6. So is this one here. 8 choose 7 is the same as 8 choose 1. So that's 8. 0.6, however, is to the power 7. And this is the power 1. And 8 choose 8 is the same as 8 choose 0. So this is 1. It'll be 0.6 to the power 8 by 0.4 to the power 0. Notice the powers always add up to 8. 6 and 2, 7 and 1, 8 and 0. And a decrease in 2, 1, 0. I think this increase in 6, 7, 8. So then it's just find these now. And 6 to the power 6 multiply by 0.4 squared, multiply by 20. Is that probability? It's 6 to the power 7. What we're doing here, we're really trying to show all our working, right? And then this one is just 0.6 to the power 8. So what is that summing up to? So the 3 decimal places 0.315. That's a lot bigger than this probability here, right? So it shows you that this is more likely to happen. In a group of 8 people, if you ask, what's the chances of more than 5 of them supporting party A? That's a significant probability. There's 31%, almost 32%. Almost a third, right? Almost a third of the population. Sorry, almost a third, 33 and a third percent, right? That's significantly more than quarter, 25%. Chances of people, less than 2 people supporting is very small, right? It's like 5%. This is how you would do these problems, okay? Hope you all understand. Look at this question now. Think about it. Assume a couple is equally likely to produce a boy or a girl. Okay, you ought to work with our probability yourself. It should be obvious what our probability is, right? But it's saying a family of 5 children, what's the probability that you have more boys than girls? Okay. Think about it. Model this as a binomial distribution. You have to say what the independent events are. What's the probability of success in one event, right? And convince somebody that this is a binomial distribution. And then phrase the question in terms of X having a value or a couple of values. Once you do that, you ought to work out the probabilities. Okay, so have fun with that. So how we do this problem is think about one trial. One trial is having a child, producing a boy or girl, right? That's one experiment. What's the outcome in that experiment? Either is a boy or a girl. You're not assuming you're having triplets and twins and that kind of thing, right? Either you're a boy or a girl, one child. Each child is either a boy or a girl. And the probability of that happening is 0.5, right? Because they're equally likely, right? That's one event. So one child being born, the probability it's a boy is 0.5, which is the same as probability is like. Now with 5 children, that's 5 events. And assuming the independent, meaning the 4th child's gender does not affect the 5th child's gender. That's what I mean by independent events. So we have independent trials happening there, right? The child you had before does not affect the child you have after. That's what we assume. And you have 5 independent events. You want to know how, what's the probability of more boys than girls? So how much boys you could have if you have 5 children? Could have 0 boys, 1, 2, 3, 4, 5. So for you to have more boys than girls, you can't have 2 boys. You had to have 3 boys or 4 boys or 5. So 3, 4, 5. So you could steal some notation from up here. You could steal all of this. Right? So consider having a boy as success. P is 0.5 and then Q is 0.5. Right? So the gender of one child does not affect the gender of the next child. So having the children, 5 of them, those events are independent. Having a boy is success, which is 0.5. So X is the random variable in number of boys. Is a discrete variable. It can have values 0, 1, 2, 3, 4, 5. It's random because the sum of the probabilities is equal to 1. So we have five events and the probability of success is 0.5. So the probability that X has a certain value A is this here. Right, and A goes up onto 5. Right? So now we could substitute that in here. This is 5, 5, 5. Right, so 5 choose A, success to the power A, and success to the power 5 minus A. So we are interested what's the probability you're interested in? The number of boys have to be number of girls. So we're really interested in X had to be greater than 2. One is probability X greater than 2. Which means what? So to have more boys than girls, either I have 3 boys or 4 boys or 5 boys. Right? And the number of boys outside of this is 0, 1, or 2. Okay, so you have to calculate 3 different things. Right? So let me see. Try and write this. With all the times. So 3, 4, 5. This one is 3. So you place A with 3 here. And A goes 4 here. A goes 5 here. So you can simplify this. This is 2. This is 1. This is 0. And then we could put the coefficients here. Where's 5 choose 3? That's 5 factorial over the product of 3 factorial and 2 factorial. So that's 4 by 5 over 2. This is 10. Right? 5 choose 4. That's really 5 over 1. So this is 5. And then 5 choose 5. This is 1. Oops. So if you watch here, 0.5 cubed by 0.5 squared is 0.55 to the power 5. So we kind of get a nice simplification here. This is 0.55 again. And this is 0.5 to the 5. So you have 10 plus 5 plus 1. This is 16 by 0.5 to the power 5. Sorry, 16. This is 6.5 is a half to the power 5. This is 2 to the power 5 is really 32. Right? Not so bad. It has 16 over 32, which is a half, which is 0.5. Right? All of that working just to get 0.5, right? But this is the correct exact answer, right? If you have 5 children, the probability you have more boys than girls, assuming boys and girls are equally likely, is a half. That's a big probability. That's 50%. 50% likelihood. Most people would take those odds and gambling any day, right? Imagine, you know, you had to throw, you had to do something, and there's a 50% chance you win the money. That's the best odds ever, right? Right? No game going to give you odds like that. All games is all kind of 1 in 1,000 or 1 in 8 billion and all kind of thing chances that you win, right? So it's a big probability. I hope you all understand how I did this problem. So this is an interesting question here. I give you this question because, you know, over the last couple of years of you being a student, guessing in exams, you know, you would have these arguments with your friends after, you know, what was the chances that you pass or fail if you just guess, right? So you could actually find the probability of guessing, or, you know, if you guess answers to questions, what is the actual probability that you get a certain score or a certain number correct, right? So if you have 10 multiple choice questions and you have 4 answers per question, and you guess for all them 10 questions, right? What's the probability you get none correct? And what's the probability you get more than 7 correct? Of course, you could generalize this to say, what's the probability you get at least 4 questions right? Or what's the probability you get exactly 2 questions wrong? You could ask all kind of questions with this, right? So I give you the first 2 then. What's the chance you get none correct? Or what's the chance you get more than 7 correct? The last one is interesting though. If you need to obtain half the marks to pass, the questions carry equal weight. What's the chance that you would pass? That's what people want to know, right? What's the probability of passing, assuming you guess for each question, right? And it's independent events. The probability of getting question 1 right, I'm not the probability of getting question 2 right. Ideally, right? The questions are not dependent on each other. So you have independent trials going on here, 10 of them. What's the probability of success in one trial? Should be easy to see from the numbers there, right? So try this out, and next time you're arguing with your friend when you all guess a multiple choice, you all will actually know the probabilities of you passing if it is you're really guessing, right? So have fun with that. Very, very practical question. Okay, so let me talk through the problem, right? So a single experiment or trial consists of guessing an answer to a single question, right? The probability of guessing correctly is is 1 on 4. Since there are 4 answers, only one of which is correct. So for one question, probability of guessing correctly is 4, 1 over 4, right? So that's a single experiment. Guessing 10 questions means repeating the experiment 9 more times. Each trial is independent of the other. Right, so guessing correctly for one question doesn't affect correctly guessing for a next question. Okay, so the independent trials repeated 10 times, right? So the same experiment is done 10 times. And probability of success is a quarter, right? So we could model this now using the language we had before. We will consider guessing correctly to be a success, right? guessing correctly is success. So guessing correctly is a success, right? So the probability of 10 independent trials, probability of success in one trial is 0.5. .257, right? That's a quarter. So X follows a binomial distribution with 10 trials and probability of success being a quarter, right? So this is enough justification here. You identify what one trial is. One trial is guessing a question. The chances of success is a quarter because there's 4 answers, one of which is correct. And then you want to guess 10 questions. So you're repeating the experiment 9 further times. So it's 10 times in all. So these trial is independent. So yeah, it had to follow a binomial distribution because you have 10 independent trials and the probability of success in each trial is the same, which is 0.25. That's why it follows the binomial distribution. So the number of questions guessed correctly. That's what X is, right? You're guessing. So we're going up to 10. We can start from 0 and we go up to 10. And this is the distribution here. Right, so 10 choose A, multiply by 2.25 to the power A, multiply by 0.75 to 10 minus A. This is the probability that X is equal to a particular value. So if you guess 2 questions right, it means 2 of the 10 were 0.25 and 8 of them was 0.75, and how much ways you could get 2 out of 10, right? So what it is they're asking for in part 1. So you're interested in probability what? They say non-correct, right? You get no question correct. It means you get wrong for all of them, right? So that is the probability that X had to be equal to 0. Right? So if X is equal to 0, then yes, you really just substitute a now. So 0, 0, 0. 10 choose 0 is 1. 0.25 to the power 0 is 1. And this is 0.75 to the power 10. Right? That's 3/4 to the power 10. So we find out 0.75 to the power 10. Right? 0.056. Essentially 0.056. 0.056. That's a small probability, right? That's like 5.5% somewhere there. That's very small. But this is the probability that no questions were right, right? You get none correct, you guess on all wrong. Now is a very small probability. That's the thing. So the probability against 0 in an exam when you guess is kind of small, you know. It could happen, but it's kind of small, right? You're bound to get one question correct. The more questions it have, you're bound to get one question right. Okay. Where's the next one? More than 7 correct. What is more than 7? So x is more than 7, right? Well, what possibilities x could have if it's more than 7? It could be 8. It could be 9. It could be 10. Because x could go up to 10. So more than 7, chances again more than 7 correct is this probability here. I took out the times. Right. So this one we 8, 8, 8. 9, 9, 9, 10, right? So 10 choose 8. That's 10 factorial over the product 8 factorial by 2 factorial. That is 9 by 10 over 2. That's 9 by 5, which is 45. So this is 45. This number is 2. 10 choose 9 is 10. This is 10. This is just to the power 1. And 10 choose 10. This is 1. 0.75 to the power 0 is nothing. So it's really just this. So 0.25 to the power 8 multiplied by 0.75 squared multiplied by 45. This is still a rather small number though. Right? A rather small number. 0.25 to the power 9 multiplied by 0.75 multiplied by 10. Still very small. And 0.25 to the power 10, oh, this is even smaller than all of those things there. Right? So this is 0.0004. And 58. That is a very small probability. That's not even 1%. That's 4/10,000ths of a percent. Right? That's real small. So you could the three significant figures, you could say 416 by 10 to the minus 4. The first one, you could do three significant figures. You know, we got 563, but these answers, you know, for very small probabilities, you want to work with three significant figures. But for not so small probabilities, like, you know, more than 1%, you could work 3 decimal places, right? So they will tell you what the accuracy to work with. So I would leave this last part here as something you could do for homework. Sorry, we'll get here. There's a probability that you pass, okay? So you could do that. It's basically just to phrase the question in terms of P of X and some value like equal something or more than equal, less than equal, something like that. And after you phrase the question, it's really just to simplify and do it, okay? Let's check our syllabus and see where we are. So we have course outline, right? So what we're able to do so far, we do everything in P1. This is statistical findings. So we are really, you know, you will get a kind of hard question where you have to look at analytical and statistical findings to solve a problem. And well, you know, merits and distinctions, if you don't get them, you could still pass. You just wouldn't pass with a merit or distinction. We talk about matrices and how to solve problems. We talk about trigonometry a lot. We talk about algebra for like 10 lectures, right? So that's kind of done. We have statistical methods. We know how to find mean and standard deviation. In your assignment, you will have a question where you have to use that to solve a problem. We talk about hypothesis testing on Thursday. You see, calculate probabilities with binomially distributed. We just finished that topic, binomial distribution. I have nothing really more to do than what we just saw there. We're moving on to normal distribution on Thursday. Right? So that's that there. So Thursday is M2 and P4. What we do, we definitely do calculus. We do all of these things, right? All the rules, integration, minima, maxima, more integration here. So we finish P5, P6, M3, D2. We do APs, arithmetic progressions. We do vector analysis, right? Resolving forces and so on, resolving vectors. You just get a hard question for this part here where you had to evaluate a question on vector analysis, right? So this is not a new topic here. This is just for you to analyze a situation with something like this here, right? When you get the assignment, I'll go over that with you. This here, dimensional analysis to solve problems. This is what we want to talk about now. What is dimensional analysis, right? The book don't really have these things, right? So you ought to kind of look at my notes for that. And this goes back to, you would have probably done this in physics, the idea of dimensions or units, right? They're related. They're two different things, but they're related. Right? So you have many formulas in the sciences, right? All kinds of formulas. Particularly in physics, you would see several formulas. Formulas always contain, well, I would say, you know, 3 or more. We could say 2 or more. 2 more quantities. Right? So you might know Einstein has a famous formula in physics, right? E equals mc squared, right? There's a formula, right? The energy given off when a mass undergoes, you know, nuclear fission or you know, converts its mass to energy, right? Is m by the speed of light squared. This is a very simple formula. It's gonna have at least two, right? Quantities, right? Now these quantities, each is measured in units. We will always use the SI system of units, right? So we have an idea of formulas, and formulas usually have quantities in them, right? Each quantity is measured in units, and we have some units in physics, we call them fundamental units, where all of base units, right? All other quantities are given units based on these things, right? Set of fundamental or base units. And in physics, the reason for deciding on these fundamental units is kind of arbitrary, right? But based on how easy they are to measure, the choice was made. So we do a table here. We could say, okay, we have quantity. You have a unit name, and we have the symbol, right? So length, mass, and time. Those are the quantities we're more from going to be using, right? But we have others that are fundamental. So electrical current is a fundamental unit. Temperature is a fundamental quantity in physics. We have amount of substance. This one is used more in chemistry. Next one is luminous intensity. So the unit name is meter, right? Length is measured in meters. Mass is measured in kilograms. This is a unit for measuring mass. Time is in second. Electric current is amperes, right? We capitalize these things because they're nouns. Temperature is usually measured in Kelvin. These are the SI units. Mole is the amount of a substance. And luminous intensity, candela. And these units have very specific definitions, based on their ability to be easily measured, right? Now the symbol, we use lowercase symbols for these things. This is kilograms, this is seconds. But for some of them, you use uppercase letters like amperes, Kelvin. Some don't have one symbol. Some use multiple symbols like mole. Mole symbol for it is MOL, and candela is CD. So these are the fundamental or base units. And you know, you would see this in a physics class. And I will talk about it in chemistry, right? These are the SI units here. Mass, length, and time. These three here are the ones that we're going to focus on in this course. But the idea is for dimensional analysis is that formulas need to be dimensionally consistent. It means what you have on the left, the units on the left, or the dimensions on the left, it must be the same as on the right. So I mean, think about it. You can't add kilograms to seconds. You know what I mean? You can't say, okay, what is 4 seconds plus 3 kilograms? What unit is that? You have to be the same units when you add it. You can multiply different units. Like this here is mass by the speed of light. You'll figure out what speed is, right? The dimensions, we can multiply different dimensions. But what's the unit for E? E is energy. Energy is measured in joules. That is a derived unit. That's not a fundamental unit. That is a unit derived in terms of the fundamental units. So if E is energy in joules, we know we're gonna figure out what the dimensions of energy are based on the fundamental dimensions here. But the right hand side better be energy too. It better be broken down to the same units as what energy is, right? So the topic of our dimensional analysis, that what we're gonna use it for, is to guess what the formula of an equation is. Guess how quantities are related together in a formula, if such a formula were to exist, right? So let's look at first proving that our equation is dimensionally consistent. So we have to do, what example is this? This is example 4. Well, I'll call it example 1, right? Because the others what we were doing were questions. So show something is dimensionally consistent, a formula. Right? First thing you have to do is we have to replace each quantity with its dimensions, and we put brackets around them, okay? So replace each quantity so what is a dimension though? What is that the dimension? We didn't really talk about that. The table just has the units, right? The unit name and the symbol. So the dimension, we use uppercase letters for the dimensions and square brackets. So we say length is L, right? Mass is M, time is T, that's the dimension, right? The other quantities have different dimensions, like, you know, temperature is theta. We tend to use theta, mole, and candela. We're not too interested in these here for now, right? So we'll come back to that just now. So replace each quantity in equation with their dimensions, right? Use the square brackets. So what is E, right? What is the dimensions of E? Energy is joules, right? How you find joules? How is energy defined? Energy is done when a force moves its point of application. So that's force by distance. And what is force? Force is mass by acceleration. And what is acceleration? Meters per second squared. You see, all these units that are derived, to find out what they are, you have to figure out what the definitions are and work your way backwards. Or, you know, you could do some research on it, right? So we could say, you know, we could say SI units energy, right? So units of energy, right? Energy is defined as work, right? The joule What is 1 joule? This is it here, kilogram meters squared per second squared. So this is where indices had a common now, all your knowledge of indices, right? The dimensions of energy, you have to convert these units here to their dimensions, right? So let's look at this here. Energy is measured joules, and the symbol is J, right? Which have units. What's the units of joule? Kilogram meters squared per second squared. So you could write that. You have different ways of writing that. Let's look at that. So you write kilogram meters squared per second squared. So we could write it like this, or we could write it as, don't write any fractions. Right? This is a more popular way of writing it here without any fractions, right? So you see it here, that's meters divided by seconds squared. This is the SI unit. They call it the joule, but the joule is a derived unit, okay? And it's, you see here, in terms of SI base units, you could always find that. And even if you go to the SI base units, you see them here? Second, meter, kilogram, ampere, Kelvin, mole, candela. The same thing I just gave you there. These are the base units in the SI system. So what is happening here? These are the units for joule, but you have to convert that to dimensions. So we come here and we say, we gotta get the units for everything, right? So that's energy. Mass is measured. So is a derived it's a derived quantity, okay? And is measured in joules. Mass is a base quantity and is measured in meters. And the symbol is M, right? C in this equation here is speed or velocity, right? Velocity is a vector quantity. Velocity obviously is a derived quantity because it's not in this table here. You know the velocity here, right? What is it measured in? Velocity is distance per unit time, meters per second, right? So it's meters per second. So we tend to do this here. Right, so we say meters per second. So you write a fraction, m over s. But it's much better to write it like this, ms to the minus 1. Now, once you know the units, right, of a quantity, any base units, right? You could always find that online. And if I give you a question with quantities, I will tell you what the SI base units are for that quantity, right? So for instance, for energy, I would tell you these are the SI units for energy. These are the SI units for velocity and so on. Now, we know it's measured in joules, right? But joules, 1 joule is, this is the derived, the unit expressed as a combination of the base units, right? So the base units constitute that derived unit there. So 1 joule is 1 kilogram meters squared per second squared. That's how you kind of say it, but you typically write it like this here because it's easier to manipulate algebraically, right? So M, right? M is the meters velocity, velocity meters per second. Now, how we're going to write this as an equation? E, if we're going to write E, we're going to take this unit here, this and convert it to dimensions, right? So the right hand side has dimensions. So it's a kilogram. Kilogram is represented, that's mass, right? So that's M, okay? Meters is length. So we write that as L and is raised to the power 2. And S is T, time. And that's raised to the power -2, okay? These are dimensions of energy, right? That's up here. The left-hand side, however, is M by C squared, right? So we write it as M is mass, right? M by C squared. Where's this thing here? This velocity. We have to write that all squared. So we put brackets around it and we say squared. We convert these units to dimensions. M, meters, is the dimension L. And S, which is seconds, the dimension is T. But that is to the power -1. And we square in that, right? So now you just use the indices here and figure this out. This 2 distributes over both of these terms. That's why we write them in square brackets. So you get a L to the power 2 and you will get a T raised to the power 2. Okay, so the 2 is, it operates on the L to get L squared, and the 2 operates on the T to get all of the squared. Now, based on our laws of indices, T to the -1, all raised to the power 2, you're gonna get basically T to the power 2. So you're gonna get this thing here. And then you could take out all the minor signs and see this is M ML right? This is supposed to be left hand, sorry, this is left hand side, this is right hand side. Sorry about that. The right hand side is M by C squared. So M by C squared. And if you notice, the left hand side dimensions is same as the right hand side. ML squared T minus 2, ML squared T minus 2. So this is the easiest thing you could do in dimensional analysis. Analyze an equation to see if it's consistent. And what we do is we take each quantity, find the units of that quantity. Like you see here, we found joules is the units for energy. Quantity is energy, the unit is joule. But we represent the units in terms of the base units. Once we get the base units, we could find the dimensions, right? Taken from this diagram up here, this table up here. And then you express each term in terms of their dimensions, and they have to be consistent, right? MC squared turns out to be energy, but how you show, how you know? In physics, they do dimensional analysis to find out what the derived quantity could be based on the combination of base quantities being multiplied. So by doing something like this, we say, okay, it's consistent. The left-hand side is ml squared t to the minus 2. The right-hand side, it turns out, is ml squared t to the minus 2. So it's dimensionally consistent. That don't mean it's correct. We don't have this equation is correct. And we don't know if it have constants or proportionality in the equation. Dimensional analysis is not all powerful. It cannot tell us certain things. I don't have a sine or a cosine inside of there, you know, cosine of some angle or something. Dimensional analysis can't tell us those things, but it can give us a prediction as to what an equation might look like, right? So from this here, another example that you all could try. So I could give you a new equation. I could say so S equals so this equation S equals a half AT squared is dimensionally consistent. S is distance, right? What is distance measured in? Measured in meters. A is acceleration. Acceleration is measured in meters per second squared. So meters per second squared, right? T is time. So just like how they give you, you know, velocity is meters per second, acceleration is meters per second squared. So use dimensional analysis to show that the equation is dimensionally consistent. Try this for homework. Next class, we'll actually show how to, not verify, but how to guess intelligently what a formula could be, what a physical formula relating quantities could be based on some observations, right? Dimensional analysis is used to guess with a high accuracy what formulas in physics could look like. So you could try that for homework.